I've mentioned several times now that many problems in statistical computing boil down to numerical linear algebra and matrix computation. So that's the topic for Chapter 2. And in particular, we're going to think about how to implement matrix computations in both an efficient and numerically stable manner. All right, so we'll start off with this problem that we've looked at already. So it's just computing the product A, B, Y, where A and B are big matrices and Y is a vector. And what we've already seen is that if you do this operation in the naive way, folding from the left, it gives the right answer, but it takes a lot longer than if you do it in the perhaps slightly less obvious way, where you use brackets or parentheses to ensure that the computation folds from the right. So why is it that one is faster than the other? Well, it's probably pretty obvious, but let's spell it out. So it's clearly to do with how you've ordered those multiplication operations and how efficient those operations are. So in the first case, we formed the matrix product AB first, and then used that matrix to multiply the vector Y. So that is, we did a matrix-matrix operation and then a matrix-vector operation. Whereas in the second case, we formed the vector product BY first. Okay, so that was a matrix-vector multiplication. But then when we multiply that, or pre-multiply that by A, that's another matrix vector operation. Yeah, so the big difference is that in the first case we had a matrix matrix product, whereas in the second case we never had a matrix matrix product. We only had two matrix vector products. Okay, and those matrix vector products are cheaper than matrix matrix products. Again, it's probably fairly obvious, but it's worth just working through the details. So let's try a couple of simple examples. So if we just think about it in the 3 by 3 case, where we can actually count things, flops are floating point operations, and so if we count multiply and add as being separate, which you might not always want to do, but let's just keep them separate for now, how many operations are involved in doing that matrix vector product? Well, if we think about each element of the output vector, it's going to, walking along the rows and down the columns, it's going to involve 3 matrix multiplications and 2 additions, okay? And so that's going to be 5. Okay, so there's 5. Oops, guess my writing's not very good. And but there are 3 elements in the output, so that gives us 15 flops involved in computing that matrix vector product. Okay, whereas if we think about the matrix matrix product, again, each element of the output is going to involve 3 plus 2, i.e. 5 operations, but now there are 3 squared, or 9 elements in the output, so that's going to give us 45 floating point operations. Yeah, so it's 45 versus 15. Okay, so we can see that the matrix product involves more floating point operations than the matrix vector product. So now let's think about this in terms of n, right? We know the basic principle now. So what about in terms of n? If we're dealing with n by n matrices and n vectors, what are the costs? Well, let's start now with the matrix product. Well, for reasons we've just discussed, if we think about each element in the output, that's going to involve n multiplications, and in principle, probably only n minus 1 additions, but let's just ignore the difference between n and n minus 1. So we're going to say each element in the output has 2n. Let's write this slightly neater. 2n operations to get each element of the output, but there are n squared elements in the output, and so that's going to give us 2n cubed. So roughly speaking, there are two n cubed operations involved in that matrix-matrix product, whereas for the matrix vector product, it's the same for each element in the output, 2n, but now there are only n elements in the output, so that's going to give us 2n squared. Okay, so they differ by a factor of n. Okay, and so when n is big, that will really matter. So the first one, I mean, we'll formalize this later. We say is an order n cubed computation, whereas the second one is an order n squared computation. And so if we think about the number of flops involved in doing this product ABY, well, if you're thinking first about ABY in the naive way, where we fold from the left, that first of all involves our matrix-matrix product, so that's our 2n cubed, and then we do our matrix vector product, so that's 2n squared, and we could pull a 2n squared out of there if we wanted, but essentially we only really care about the leading term, which is this 2n cubed. Okay, that's going to dominate. Whereas if we do it the other way, the first operation is the product by, which is only 2n squared, and then the other operation is going to be the same. So it's just going to be 4n squared. Okay, so the second way of doing it is as leading term 4n squared, whereas the first way is of order, is roughly 2n cubed. And so one of those is n cubed, one is n squared. For big N, obviously, the n cubed one is going to involve many more operations than the n squared version. Okay, and so that's why it's much better in this case to fold from the right. Okay, so there's a sort of general principle there, which is that you can, roughly speaking, count the number of operations involved in the different ways of doing calculations. And so if there are different ways of doing them, you can think about which is going to lead to the smallest number of floating point operations. And that's going to correlate reasonably well with the actual amount of time taken to do those operations, though in fact not perfectly for reasons we'll explore a little. Okay, so let's see this in another example. So now we want to compute the trace of the matrix AB, where A and B are big matrices. But this time A and B are not going to be square matrices. So A and B is going to be 5,000 by 1,000. B is going to be 1,000 by 5,000. And there are a bunch of different ways we could compute this trace. Okay, so how could we do it? Well, in the first way, we just do probably the obvious thing. So we form A times B, we take its diagonal, and we sum the diagonal elements. So that's more or less the definition of trace. Okay, so that's probably what you would do if you weren't really thinking about it. However, one of the properties of trace is that the trace of AB is the trace of BA, and here that is going to be much better, because BA is going to be 1,000 by 1,000, whereas AB is going to be 5,000 by 5,000. Yeah, so that first naive method was going to involve the construction of a 5,000 by 5,000 matrix, whereas this second method is going to involve the construction of a 1,000 by 1,000 matrix. So that is fairly obviously going to be better. In fact, there's an even better way to do it, which is not to involve creating those products at all. It's just to take our matrix A and just do element-wise multiplication by the transpose of B, and then sum all of the elements of that resulting matrix. We'll see why that works in a second, but just trust me for now that these three different ways of computing the trace are all correct. Okay, they all give the right answer, but they are not all of the same efficiency. They don't all involve the same number of flops. Okay, and here, just to illustrate this benchmark package once more before I revert to using system.time for most of the rest of the course, we see that this final method is the fastest if you just look at the elapsed time here. If we look at them relative to that final method, so we make that 1, we see that the slightly more intelligent way of doing it takes twice as long roughly, and the very naive way of evaluating the trace actually takes 10 times longer than the really smart way of evaluating the trace, right? So these things really can make a difference, yeah? So it's not just a matter of taking your mathematical expression and kind of literally translating it into code. Whenever you've got a non-trivial matrix computation, you really need to think about, what am I doing here? What are the different ways I could compute this thing, and which are more efficient in terms of the number of floating point operations involved. And if you pick the method that has the smallest number of floating point operations, that will typically be the fastest. Okay, so let's just make sure we do understand this and why it works. So the naive method had a cost of 2n squared m. The second method relied on the fact that the trace of AB is the same as the trace of BA. If we then just work out the flop cost, it's now 2nm squared, and because here n was bigger than m, then that's going to be smaller. But the third method, okay, is perhaps the least obvious, and that's just directly writing out what the trace of AB is, and if you kind of slog out the algebra, you quickly convince yourself that it's simply the sum of the element-wise products of Aij and Bji. That's what we calculated, and if you work that one out, you see that it actually comes at a cost of 2nm, okay? And so that's an order lower again, okay? So in principle, this one is the fastest. However, this one does involve computing the transpose of that matrix B and doing that element-wise multiplication, and that might not be a cheap operation either. So it's not always completely obvious which method will be best, but here if it's a whole order faster as it is here, then it's a pretty good bet that it's going to work out the fastest. Okay. And yeah, and just to emphasize as well that it's not necessarily just about flops. It can also be about memory and storage. And that first method was bad not only in terms of the number of flops, but also because it involved the construction of a 5,000 by 5,000 matrix, which was clearly completely unnecessary. The other methods did not require the construction of a 5,000 by 5,000 matrix, and if you can avoid doing that, you definitely should avoid doing that. Okay, so just generally, this is the kind of thing one can do. It'd be really, really tedious to track exactly how many floating point operations are involved if you're doing anything non-trivial, but what you generally do is just keep track of the leading order terms, okay? So here, if you're doing your trace computation, in fact, if you very, very carefully counted the operations, you'll find it wasn't a simple n squared m. It was actually more complicated than that. But we just looked at the first term, right? Because that was the only thing that mattered. And so we say it's of order n squared m. So this order notation is a standard notation. It's used a lot in computing science. It's used a little bit in mathematics as well. And this is a big O, okay? So just to be aware that for this order notation, there's big O and there's little o, and big O, generally speaking, just means it's of roughly that order. Yeah, it goes like, yeah, so we'd say that the number of operation goes like n squared m, okay? So that's your order notation. So usually if you just track the highest order term, you can usually figure out what's going on without getting too bogged down in minute details. Another thing really worth knowing, though, is that not everybody counts flops the same way. So when we were doing those matrix vector products and matrix products, we were counting multiplication and addition as two separate operations. But in fact, many people would count a multiply followed by an add as one floating point operation. And there are very good reasons for doing that. So one is it makes things a little bit simpler to track. But the other is that actually the way a lot of modern chips work, and multiplying and add is a single atomic floating point operation, and so it actually, makes more sense to count that as one flop. So just be aware that some people would count a multiply and an add as two separate operations, but many people would actually just count them as one operation, and that makes your tracking flops even simpler. However, I sort of suggested that usually the flop count gives you a good idea of how long an operation will take, but it really isn't quite as simple as that. Modern computers are very, very complicated. There's an awful lot going on under the hood, and so it isn't necessarily as simple as that. And so one thing to be aware of is the fact that just indexing and manipulating data in memory also take a lot of time and effort. So I mentioned in passing that the fastest method of computing the trace involved the fewest number of flops, but it did involve transposing a matrix, and that's not necessarily a cheap operation either, right? So that's an example of something that would be easy to ignore, but actually really matters. But there are other things as well, just indexing. So here, if we just use C notation, because there are so many things going on in R that who knows what's actually going on, but in C at least you know what's going on. So here's an example of doing just a product. Okay, so this is one flop in the sense that it's multiplying one floating point number by another floating point number, but actually that isn't the only operation that's going on. There are a lot of integer operations going on. So to multiply those two numbers together, you first of all have to retrieve them both from RAM. Okay, so this AIK is indexing a place in memory where this number can be found, and similarly BKJ is indexing a place in memory where this number can be found. And so actually just figuring out exactly where these numbers are, locating them, fetching them into the CPU so that they can be multiplied. These all take time and effort. So there's a lot more going on than simply multiplying the numbers together, and this can make a difference too. So how your data is arranged, how it's indexed, how you are indexing into it, all of these things can make a difference in some situations. So you kind of hope that in many situations it doesn't really matter, but it's worth being aware that it can matter. Okay, so there are kind of indexing issues underlying all of this as well. But actually, the thing you really need to know about is the fact that although your matrices are stored in RAM, and RAM stands for random access memory, that means you can access it randomly. Okay, so you can just go in there and pick anything out of it at any time. It's actually a very slow operation to do that. Compared to the time, say, it takes to multiply two numbers together, the time it takes to just pick a value out of RAM and bring it in is very long in comparison to that time. And so what modern chips do is they have cache, and they have more or less complicated caching systems depending on the chip. Often these days they have very complicated caches with level 1 cache and level 2 cache, and then going out to RAM, etc. But they have a caching mechanism. So what does that mean? Well, what that means is if you're multiplying and adding a bunch of values, as you are when you're doing a matrix vector product, when you request a particular value from memory, the processor typically doesn't just get that value. It gets that value and maybe the next few values as well, and brings them all into the CPU and keeps them in the cache. Okay, and that means that if you then ask for the next value, the CPU says, aha, I've already brought that into the cache. I can just bring that in from the cache. I don't have to go all the way back to the CPU to get that. Yeah. But what that means is that as long as you are doing your operations in a way that is accessing memory sequentially, then your operations are very fast. But if you are accessing memory in a way that doesn't align well with the caching strategy, then your algorithm will be relatively slow, even if it involves in principle the same number of floating point operations. Yeah, and so doing things in a cache friendly way turns out to be extremely important if you want to do floating point computations very fast. But of course, this is a very delicate thing, and it varies from processor to processor exactly what the best way is and how big your chunk should be and things like that. So you don't really want to be worrying about this kind of thing yourself. Fortunately, you don't need to, because it's essentially all been done for you. And so the kinds of operations that we've been looking at, things like matrix multiplications, matrix vector multiplications, matrix additions potentially, etc. They are all what are known as BLAS operations, right? BLAS, it stands for the basic linear algebra subprograms. And higher level functions, such as, say, doing an eigen decomposition, computing eigenvalues and eigenvectors, that sort of thing, those higher level operations, they will be provided in a higher level library like LAPACK or LINPACK, which in turn uses BLAS to do the lower level operations. Yeah, so you got BLAS kind of sat near the bottom, which does these super efficient basic matrix computation operations. Then on top of that, you've got LAPACK or LINPACK or something that provides higher level routines such as eigen decomposition, Cholesky decomposition that we'll look at in a second, etc. And on top of that, you've got kind of your code or another language such as R sitting on top of that. And so when you do an operation in R calls maybe the LAPACK routine and LAPACK calls the BLAS routines. But one way or another, all of these low-level operations are being carried out using very fast, efficient routines that have been very carefully written in order to do things like lay things out in memory in a sensible way, do the operations in a cache-friendly way, so you really get the best performance you reasonably can for those sorts of operations. Okay, and in fact, yeah, as it mentions at the bottom here, some of the latest versions of these libraries will even exploit the fact that you've got typically multiple cores on most machines now, and so some of them will even multi-thread and parallelize some of these matrix operations for you. Okay, so it really is worth making sure you are using a good modern BLAS that is well suited to the computer that you're running on. Okay, so whatever you're doing, you want to use BLAS and LAPACK to do your low-level matrix operations. It's worth making sure you've got a decent one. So as it says here, sometimes if you just kind of use the default one that comes with your operating system, it's maybe not highly optimized for your machine. And so you may want to investigate using a better, more efficient BLAS or LAPACK library. It can make a difference. Okay, so these days, if you're using a modern OS, it'll usually come with a decent one, but it's worth playing about with, making sure you've got a fast one, because if you're doing lots of matrix operations, it really can make a difference to your runtimes. If you're in a situation where you have multiple BLAS and LAPACK libraries on your computer, which often happens if you start going down this route, then sometimes you might wonder which BLAS and LAPACK library that R is picking up if you're trying to do stuff inside R. Well, there are these commands here that, at least on Linux, will tell you which LAPACK and BLAS libraries are being picked up by R. So that can be very useful to know. So if you've got multiple ones installed, just to make sure it's picking up the one you want it to and not some old useless one you've got lying around. Okay, so that's a useful thing to know about. But like I say, this works on Linux, but it doesn't work on Windows. I don't quite know what you're supposed to do on Windows. Okay, so in terms of thinking about efficiency then, the take-home messages are: think about the flop count when you're computing with matrices, or computing in general, in fact, but particularly when you're computing with matrices, it's particularly relevant there, because different ways of doing essentially, the same operation from a mathematical point of view really can make a big difference. But just be aware that there are other issues other than simple flop. So memory management, how you lay out your objects in memory, how you write your algorithms to kind of index and run over the objects that you have laid out in memory can matter as well. And that's just something to be aware of. And if you don't want to have to worry about those kinds of low-level issues, do make sure that you're using a good LayPack and BLAST library wherever possible. You really shouldn't be writing your own low-level matrix operations yourself. These implementations provided by BLAST will almost certainly be many times faster than anything you could write yourself naively. Okay. So that's a little bit about efficiency and flop counting. But now we're going to move on to think, start to think about more sophisticated matrix computations, and in particular, how to do problems involving systems of equations and solutions of systems of linear equations in a numerically stable way. Okay, so to avoid some of those pitfalls that we saw in the last lecture. And for that, we need some common notation. So there are lots of different flavors of matrices. So a square matrix has the same number of rows and columns. For a symmetric matrix, if you reflect it in the diagonal, it looks the same. Okay, so the elements above and below the diagonal look the same. That turns out to be a very important class of matrices. Related to that, in fact, is the notion of a positive semi-definite matrix, which simply has a positive definite or positive semi-definite. So a positive definite matrix has the property that for any y, vector y that you choose, y transpose xy gives you a strictly positive real number, and the semi-definite case is greater than or equal to 0. So that turns out to be an extremely important property that we typically think of in the context of symmetric matrices, though we don't have to. Another important notion is the notion of a triangular matrix. So a triangular matrix has elements either above or below the diagonal, all being 0. So a lower triangular matrix just has elements in the lower triangle. Everything above the diagonal is 0. Upper triangular is the converse. Triangular matrices are super useful in the context of numerical linear algebra for various reasons, but in particular because solving linear systems involving triangular matrices is much easier, faster, more efficient, more numerically stable, etc., than solving arbitrary linear systems. And so if you've got any kind of linear algebra problem where you need to solve the system, effectively invert a matrix, although usually without explicitly inverting a matrix, just solving linear systems, solving them involving triangular matrices is much easier. And so we'll see why that is shortly. But triangular matrices are very important in numerical linear algebra. And of course, the special case of a matrix that is both upper triangular and lower triangular is called a diagonal matrix for obvious reasons. One final notion that turns out to be really important is the notion of an orthogonal matrix. We'll see why they are so interesting in the context of numerical linear algebra as we go along. But just to note that it has the property that Q transpose Q is the same as Q transpose is the same as the identity. So what that means is that Q transpose is the inverse of Q. And in particular, it means that Q must be square. But the point is that Q is a matrix such that its transpose is its inverse. And so again, you can imagine various reasons why that might be useful. But in particular, it's a very simple matrix to invert, right? Because you just form its transpose and you've got its inverse. And again, in general, inverting is a very difficult and unpleasant operation. And so the fact that orthogonal matrices basically come with their own inverse for free is at the heart of why they are very useful in the context of numerical linear algebra. Okay, so we're going to start off with a particularly useful matrix decomposition in the context of statistical applications. Yeah, so there's all kinds of areas where numerical linear algebra is important, but in statistics, we tend to find ourselves working a lot with square, symmetric, positive definite matrices, and in that context, the Cholesky decomposition turns out to be a super useful notion. And it's a kind of square root. So let's think about that. So I guess the first thing to say is that that in some sense, positive definite matrices are like positive real numbers. Okay, and we'll sort of make that a bit more precise as we go along. Covariance matrices, or variance matrices if you prefer, are usually positive definite and always positive semi-definite. Okay, so this is one of the reasons why in statistical applications this notion of a symmetric positive definite, or at least positive semi-definite matrix crops up a lot. Okay, we're going to start off by thinking about strictly positive definite matrices and what a square root might be and why a square root might be useful. So let's just think about that first. So let's start by thinking about a multivariate normal random variable. We maybe know how to simulate from standard normal scalar random variables, just random normal 0-1 deviates. I mean, you may have studied that before. If not, it doesn't matter. But there are very simple and efficient ways of doing that. But what if we're interested in an arbitrary multivariate normal random quantity with mean vector mu and variance matrix sigma? What then? What if we wanted to simulate values from that distribution? Well, just by stitching together a few IID normal 0-1s, we can easily generate vectors z that are multivariate normal in the trivial case of a mean vector that is 0 and a variance matrix that is the identity. Okay, that should be clear, I hope. So we have a way of simulating vector z from that very special multivariate normal distribution. If you think about it, if you could find a matrix R such that R transpose R was equal to sigma, okay, and it's maybe not obvious that you can do that, but let's just go with it. Okay, so suppose you could find a matrix R such that R transpose R was sigma, then in fact it's pretty clear that if you multiply Z by R transpose and add mu, if you think about what the mean vector will be and what the covariance matrix will be, well, the mean vector will be just mu, okay, and the covariance matrix will be R transpose R, but by kind of assumption we've said that will be sigma. Okay, so if we could do this kind of square rooting operation, then we would have a way of generating these multivariate normal random quantities. Okay, so this is a kind of a square root, but it's a little bit of a funny square root, because you might imagine that a square root of a matrix would be a matrix such that R squared was sigma. Yeah, so that would be a more obvious way of defining a square root. You can define a matrix square root that way. It turns out that especially in statistical applications, a sort of more general and more natural way of defining a square root is the way we've just defined it. If this matrix R is symmetric, it obviously is the same thing, and we'll come back to that later. But just go with it for now. A natural way of defining a square root of a matrix, especially in these sorts of statistical contexts, is to define it as a matrix such that when you multiply it by its transpose, you get the matrix that you started with. Okay, so that's all good. If we could find a matrix R that had that property, we would be good, all right? And that's a particular way of decomposing sigma into a product of two matrices, yeah? So instead of taking two matrices and multiplying them together, we're taking a matrix and we're pulling it apart into two factors or that compose together to give you the matrix you want. So how do we do that? Well, in general, that system we've just described doesn't have a unique solution, right? It has lots of solutions. There are lots of ways you could find matrices R that satisfied that property. In fact, there's only one that is symmetric. So we'll see later how to find the symmetric square root. But if you drop the symmetry requirement, then there are lots of ways you could do it. If you think about the degrees of freedom, there are only the number of degrees of freedom that you would have in a triangular matrix. Okay, and so a natural question is, can we find a triangular matrix R with that property? Yeah. And so that is what the Cholesky decomposition is. If you think about the degrees of freedom, they add up. So maybe this is a good strategy to try. And as I've previously mentioned, triangular matrices have lots of nice properties in the context of linear algebra. So maybe this is a good strategy. Well, it turns out it is a good strategy, and this is the so-called Cholesky decomposition. So there are two ways of defining the Cholesky decomposition. So one is using the upper triangular square root R. So then the decomposition is R transpose times R. Gives you the matrix you're interested in. But we could actually just focus on the left-hand matrix here, this lower triangular matrix, and call that the Cholesky triangle. And then your Cholesky decomposition is L transpose is equal to the matrix you're interested in. Okay, so both of those are commonly used. In fact, the LL transpose definition is slightly more common in the literature. The reason we're going with the R transpose R definition here, the upper triangular formulation, is mainly just because that's what R returns. So if you ask for a Cholesky triangle in R, it gives you the upper Cholesky triangle. So it makes sense for us to go with that notation here. But it's exactly the same. It's just which you call the Cholesky factor. Okay, so how can you solve this system, right? We've got the right number of equations, so can we solve this or not? Well, it turns out we can. We just try it one equation at a time. So we focus first on the first element of the output, A11, and we say, well, how do we get A11? Well, it's just R11 squared, okay? So there's only one unknown in that. So we just solve that for R11, and then we think about, okay, well, let's think about A12 next. How do we get A12? Well, again, we just do the product and we write it down, and we see that actually it involves R11, but we've already worked that out. So the only unknown here is R12, so we can solve for R12. And we work through the elements of this A matrix one at a time, go through them in order, and we find that at each stage we only have an expression with one unknown, because all of the other potential unknowns we've already worked out. Yeah, and so we just get a sequence of equations involving one unknown that can be trivially rearranged to give us that one unknown, and that gives us all of our R values, which gives us our upper triangle, our Cholesky factor for our Cholesky decomposition. Okay, so if you just turn that into equations, we got a very, very simple algorithm here. Okay, so we've got a very, very simple algorithm where we just work through the matrix one element at a time and compute the R values that we need. Okay. So that is the Cholesky decomposition. As it says here, it is an n-cubed operation, as a lot of these decompositions are, but it's a relatively cheap n-cubed decomposition. Okay, so here it's roughly n-cubed over 3. Okay, so it's a relatively cheap n-cubed operation, relatively numerically stable, and it gives you a triangular matrix, which turns out to be very, very useful in lots of contexts. Okay, so again, you don't have to code this up yourself. It's performed by the chol function in R, and the chol function in R calls out to LAPACK, and the LAPACK probably calls out to BLAS, etc. Okay, but the point is, there's just a function in R that will give you this Cholesky triangle. You don't need to write it yourself. Okay, so how does that work? Right, well, let's go back to that example of simulating multivariate normal random quantities. Suppose we wanted to simulate random vectors from this particular multivariate normal distribution. Well, we can define the variance matrix, we can define the mean vector, And then what do? We form the Cholesky decomposition of the variance matrix. And like I said, in R, you get back the upper triangle that we have called R. So that's all good. You then simulate your Z values just as 3 IID standard normals. You then form the transpose of R times Z plus mu. And that gives you your Y. Okay, simple as that. And so there is your random vector. Okay, how do you know that that's really worked? Well, the best way to know whether it's really worked is to do lots of them. Okay, so let's generate 1,000 such vectors by putting the Z values as columns of a matrix and just doing the relevant matrix operations to construct a matrix of Y values. And then what do? Well, we can look at the row means, make sure the row means look about right, and they do. It's roughly 1 minus 1, 3, so that's about right. And then we can look at the observed variance covariance matrix, and again that looks about right. It's roughly 2 minus 1, 1, etc. Okay, it's not perfect, it's just a Monte Carlo sample of size 1,000, but it looks like this has done the right thing. Yeah, so by using the Cholesky decomposition of the variance matrix, we found a way of simulating multivariate normal random quantities with a given variance covariance matrix. So that's a useful thing in its own right. But the fact that this Cholesky factor is a triangle is also useful for ways that we'll see in a minute. Okay, so let's have another look at why this Cholesky factor might be useful. And again, it just relates to looking at the Cholesky decomposition of a variance covariance matrix, right? So that's nearly always where it crops up in statistics. Not always, but nearly always. So now let's suppose we want to evaluate the likelihood or density of a multivariate normal random vector. As usual, we tend not to work with raw likelihoods or raw probability densities. We nearly always like to work with log likelihoods and log densities for various reasons. And we'll sort of discuss some of them along the way, but they're more floating point friendly, less likely to underflow or overflow your floating point representations. The behavior of the surfaces is nicer, better behaved. A likelihood function is likely to be more convex if you look at its log, etc., etc. So there are lots of reasons why we like to work with logs of likelihoods rather than likelihoods. So if you write down the log of a multivariate normal density, then this is what it looks like. And so what does it involve? Well, it involves a log of a determinant. Okay, so that's an interesting thing to think about how to compute. And it involves this quadratic form here that involves, at least on the surface, inverting the variance covariance matrix. Now, we don't have to invert that matrix for all kinds of reasons. We simply have to solve the linear system, sigma x equals y minus mu, say. However, even that would be an arbitrary linear system, and we'd rather not solve that. So how can we do something smart to evaluate this? And can we get the determinant as a byproduct? And the answer is yes. So basically what we're going to do is try and exploit this Cholesky decomposition. Okay, so if we know the Cholesky decomposition of sigma, then just by inverting that, we get this decomposition of sigma inverse. Okay, so we have a decomposition of sigma inverse as well, but in terms of the inverse of the Cholesky triangle. So do we have to invert the Cholesky triangle? Well, no, we don't. We just have to solve a linear system. So let's just keep going. But it's pretty clear that given that decomposition, all we need for this final term here is Z transpose Z, where Z is R transpose inverse, is what that notation means, y minus mu. Okay, so if you just take that as your definition of Z and calculate Z transpose Z, you'll see that what you end up with is this quadratic form here. Okay, so that's all good. We don't have to explicitly invert R transpose here. What we do is we say this is just the solution Z of the linear system R transpose Z is y minus mu. So this is the solution of a linear system, which you could do by inverting, but that would be a bad idea, especially here because R is triangular. Yeah, so R is upper triangular, so R transpose is lower triangular. So what we have is what we've got at the bottom here, which is this lower triangular linear system that we want to solve for Z. Okay, so we know everything at this point except the number Z. So how are we going to solve for those numbers Z? Well, it turns out that because this system is triangular, that's an incredibly easy thing to do. Because if you just look at the first equation, okay, it's just R11, Z1 is Y1 minus mu1. So it's easy to solve that for Z1. Similarly, for Z2, that's going to involve Z1 and Z2, but we already know Z1. So just like for the Cholesky decomposition, we're going to have a sequence of equations where there's only one unknown. Okay. So if we write them out like this, we see that at each stage, we just work our way forwards through that system of equations, solving for the one unknown at each stage and substituting in for the other things that we've already solved for. Okay, so this process is called forward substitution, and it's an n-squared operation. Okay, so this is much cheaper than explicitly trying to compute the inverse of a matrix, and it's also incredibly stable, and it's roughly the same cost as the matrix vector multiplication. Yeah, so it's actually no harder really to do this forward substitution process than it would be to form a simple matrix vector product involving a triangular matrix. They're both essentially the same operation, and it's pretty numerically stable as well. So this is a good operation. Okay, so it's a good, fast operation, forward substitution. So solving triangular linear systems like this is very simple and straightforward. And so here we've solved this problem very, very straightforwardly. Okay, so this is called forward substitution. In R, there's a function called forward solve, which does forward substitution for you using a lower triangular matrix. If we had an upper triangular linear system to solve, in that case, you start at the bottom with the very last element and work your way up. Okay, so that's called backward substitution, and there's a function in R called backsolve for doing that as well. We still haven't figured out the determinant as sigma, but actually this is easy as well because we know it's just the square of the determinant of R, and we know the determinant of R because R is upper triangular, and so the determinant is just the product of the diagonal elements. Yeah, if you've got a triangular matrix, again, one of its really nice properties is that its determinant is just the product of the diagonal elements. And so it's trivial to work out the determinant of a triangular matrix, which is good because determinants are nasty to work out. Okay, so we also get the determinant from the Cholesky factor as well. Okay, so putting that all together, once we've got our Cholesky decomposition, we just find our z's by a single forward solve operation. Then we can just put things together with a sum of the log of the diagonal elements to get our log determinant, and we get our log likelihood in a very cheap and numerically stable way. Okay, there's no explicit inverting of anything. There's no kind of nasty determinant calculations. Given the Cholesky decomposition, we can calculate this likelihood in a very efficient and stable manner. Okay, so far we've been assuming that our matrix that we're interested in doing the Cholesky decomposition of is a strictly positive definite matrix, right? That means like no zero eigenvalues. If the matrix is only positive semi-definite, and some covariance matrices are, yeah, so we're typically thinking about variance covariance matrices here. a variance-covariance matrix is guaranteed to be positive semi-definite, but it's not actually guaranteed to be positive definite. It could have some linear combinations that have zero variance. In that case, it has zero eigenvalues. And in that case, the straightforward sort of naive Cholesky decomposition will fail. Okay, so there's a question of what you should do in that case. In fact, you can modify the Cholesky decomposition process slightly in order to figure out what is effectively the Cholesky decomposition in that singular case. In fact, in statistical applications, that's not normally what people do. People generally use a different decomposition, and there are various other decompositions that we're going to look at, but that is the topic for the next lecture. So we'll start off, looking at the symmetric eigendecomposition. That will give us a symmetric square root, and that symmetric square root will also work perfectly well in the case of a positive semi-definite matrix that is singular. Okay, so that is the simplest solution to this problem, but in fact there are many others, and there are pros and cons, but I think this is a good time to break.